All right, so again, one more quick problem here to sort of calculate voltaic cell sort of information using Appendix D, but this one's a little bit different. Do you remember sometimes when we did stuff with Hess's law, sometimes we'd have to look up everything, or if we did standard heats of formation, sometimes we'd have to look up everything on Appendix B, and then we'd sum it up all to make an overall delta H of reaction, right? But we had a few problems where maybe we were given delta H of reaction and we had to find the delta H of formation for one of the species that was there. So for example, this problem that we did here, we had to calculate what the overall was, and we had to look up each of the individual pieces. Can you see that for this problem, they've actually given us the overall, and they've given us one of the half-cell. Now, actually, if you actually looked this up on Appendix D, you'd actually see that it's the same value. But they want us to calculate the E for bromine. Okay, so now we have to figure out that unknown. So see if you can figure out and sort of work through this different permutation, if you will, of sort of our E cell reactions, and see if you can figure out how to calculate E for bromine. Pause the video and try to sort of work through it yourself, or again, let the video play if you kind of want to just see a worked out solution. As a hint, the first thing that I want you to do is try to split up this reaction into its corresponding two half reactions. Okay, so if we split this up into its corresponding half reactions, we're going to have here our reduction reaction here, right? We've got bromine going to bromide, which means it's got to gain electrons. We've got zinc going to zinc 2+, that's our oxidation reaction. Don't need to do any scaling here because we've got 2 electrons that are being traded there. They told us that the E for zinc, again, was going to be negative 0.76 if it was a reduction potential, right? And again, if we looked it up on Appendix D, we would see this value, but we're making it into an oxidation half reaction, which means we're going to change the sign, flip the sign. They told us what E cell was. E cell is E reduction plus E oxidation. So again, we know the oxidation piece and we know what they sum up to, but we don't know this piece. So see if you can finish out this problem to figure out what this missing piece is. All right, pretty straightforward here. We just sum up everything, right? Sum up everything, we get to our overall equation. Sum up everything, we know that everything needs to sum up to positive 1.83. So if we need to sum up to positive 1.83 and we already have 0.76, just a little bit of algebra will allow us to figure out what this guy is. So again, positive 1.83 equals our standard reduction potential plus the oxidation potential, which we already know. And so just solving again for this unknown tells us that the E reduction for bromine is going to be 1.07 volts. All right, so last problem to work through here. This is actually going to be kind of 4 problems in one, because first we're going to actually calculate or think about the relative strengths of each of these as oxidizing and reducing agents, and we'll talk about how to do that. That's going to be kind of like a part 1 sort of problem. You know, who is the strongest oxidizing agent? Who's the weakest reducing agent? And so forth. And then we're going to label these reactions A, B, and C. And we're going to look at the different combinations we can have for creating different half cells. So just to kind of set this up, we can have an A-B reaction, we can have a B-C combination, or we can have an A-C combination. So we're going to create half cells by mixing those different sort of possibilities together and see what we come up with. So it's kind of, 3 problems in one in that regard. But the first thing that we're going to do is think about sort of tackling this question. Who is the strongest oxidizing agent? Who's the strongest reducing agent? So I'm going to walk you through this problem because it might be a little bit difficult to just kind of throw at you. So see if this makes sense here. Right now, I have identified in green here things that are reduced, right? These are species that are reduced, right? Because they're on the left side of a reaction that's gaining electrons. So these are things that are being reduced, which means they are oxidizing agents. These guys over here are species that have become reduced. So again, if we're thinking about the reaction going in the opposite direction, these are going to be species that maybe likes to be oxidized, okay? Because if we're going to go in this direction, that means that we're going to be giving up electrons. So remember, anything that's gaining electrons is something that's being reduced. Anything that would be giving up electrons is something that's being oxidized. Okay, so we've got 6 things here that we've got to rank. The things that are in green are the things that are being reduced. The things that are in red are the things that are going to be oxidized if we consider the reverse reaction. Okay, so hopefully everybody's okay with me. What we need to do now is recognize that there's sort of a ranking here. Remember, the more positive an E value is, the more that reaction likes to go in that direction as written. So we can kind of see a ranking here. This is sort of the most positive E, then we've got this guy, then we've got this guy. So what this means is MnO2 most likes to gain electrons. So again, if we want to think about the strongest oxidizing agent, that means it's the guy that most likes to be reduced and gain electrons. Based on the standard reduction potential, it's this guy right here. So MnO2 is the strongest oxidizing agent. Then the next one kind of ranking here is this first reaction. So NO3 is going to be the next guy in terms of liking to gain electrons. And what we actually really have here, this guy really doesn't like to gain electrons. We've got a standard reduction potential that's negative. So in terms of ranking these 3, here's the order that we'd put them in. Most likes to gain electrons, still likes to gain electrons, doesn't want to gain electrons at all. Now let's look at the flip side. Let's look at these in terms of oxidation reactions, remembering that something that is going to be oxidized is a reducing agent. So in this case, we want to think about, again, looking at if these were positive E cell values, which of these most likes to give up electrons, right? This is going to be the most positive E going in that direction, right? So this guy most likes to give up electrons. And if we actually were to look at E's for these 2 reactions, again, they'd be flipped if we're looking at them as oxidation reactions. Then going in order, this guy's going to be next, and then this guy. So N2H5 plus most likes to give up electrons, then NO, and then Mn2 plus. So again, that's a little bit of a kind of a difficult concept to think about, but again, a really important skill. You're going to see questions where you're going to sort of rank or see a laundry list of things, and you're going to be asked, who is the strongest oxidizing agent or the weakest reducing agent? Okay? All right. So again, if we want to think about sort of putting these reactions together, right? And I'm going to label them A, B, and C here. I'm going to kind of put that back over here. We've got A, B, and C that we have here. If we're thinking about kind of making spontaneous reactions, hopefully it makes sense that we're never going to have a situation where this guy becomes a flipped reaction. We're never actually going to take C and flip it, because that would make this being minus 1.23. And neither of these reactions could compensate for that. So this reaction is always going to be in this direction. Okay? We can't flip it and then compensate for that negative 1.23 volts and end up with a positive E cell. Okay? So keep that in mind. What we're going to run through now is our different combinations. All right, so let's think about our A-B combo. Okay, so this was the reaction that I labeled A and B over here. So I've just sort of rewritten them here. I want you guys to put these reactions together so that we have a positive E cell and tell me what the overall chemistry is going to be for that reaction. So again, I want you to pause the video and see if you can figure out how would we create and what would the voltage be on a spontaneous reaction for these 2 processes. All right, so again, bringing in some stuff that we actually had to learn in our first lecture here. We also have to make sure that we're scaling things appropriately with the right numbers of electrons. Notice that's not going to change what we have over here. But hopefully it makes sense to everybody that this is the reaction we want to flip. Because flipping this and making it negative 0.96, that's not going to help us at all to have a positive E cell. But flipping this guy certainly will help. So this is the guy that needs to be flipped, and we actually need to scale these quite a bit in order to have those electrons cancel. So the first reaction needs to be scaled up fourfold, remembering we do not scale the standard reduction potential. Our second reaction gets flipped, so it becomes an oxidation reaction, so we change the sign on that value, and then we need to scale that guy by threefold. That allows 12 electrons to be exchanged between these guys. And then when we allow those electrons to cancel and we reconcile protons being on both sides here, we sum them up to get this overall kind of reaction. Pretty messy reaction, lots that we have there. But again, E cell is going to be the sum of these two kind of potentials that we have here, an oxidation and a reduction potential. Overall, this is going to be positive 1.19 volts. That's a spontaneous reaction, positive E cell. All right, I want you guys now to try the AC combo. See if you can figure out who gets flipped here, how do we scale, what's our overall final redox reaction, and what's the value of that E cell. So pause the video, try to work through this one. All right, remember when we talked about this C reaction, we said this guy's never going to be flipped because we couldn't compensate for that negative 1.23 volts. So this is the guy that needs to flip up here. So again, we're going to flip this. And again, we note that we need to flip that one because that's what allows us to have a positive E cell. So again, flipping this guy, we need to scale the first reaction up by 2, the second one up by 3. Remembering we do not scale the potential values here. Got to reconcile protons and water that we have here. Here is the final balanced chemical reaction. So again, we're practicing some skills from our first lecture there in balancing redox reactions. Bringing in kind of the new component here, we're going to add up the accompanying potentials for the reduction and oxidation half cells. And again, this time we have a negative value that we have here. But again, adding a negative value is like subtracting it, so we end up with positive 0.27 volts. All right, last combination to try. And again, if you haven't gotten the first two, hopefully you feel comfortable enough to take a stab at this one. Pause the video and try to work through the BC combo with these two reactions. Figure out what the overall balanced chemical redox reaction is, and then what E cell would be for this voltaic cell. All right, again, this is the one that needs to flip. We cannot flip. We're never going to see this guy get flipped. So flipping the first reaction, and again, we don't need to scale that first one. We just flip it here. And then we do need to scale the bottom reaction by twofold so that we have an even exchange of electrons there. Kind of reconciling things that appear on both sides to balance our chemical equation. Here's our net final balanced chemical equation. Adding our oxidation and reduction potentials here gives us an overall E cell of positive 1.46 volts. Now, one of the things I kind of want to highlight here as we kind of wrap up here is this is what we might call the winningest combination. Looking back, this one has the most positive E cell, 1.46, 0.27, and 1.19. So that was the most favorable E cell. Okay, not surprisingly, it had the strongest reducing agent paired with the strongest oxidizing agent. So look here. Remember these two guys, N2H5 plus and MnO2. I'm going to flip back to when we figured out who was the strongest reducing agent and the strongest oxidizing agent. So the strongest reducing agent was N2H5. The strongest oxidizing agent was MnO2. So it's no surprise that mixing those strong combinations would give us the battery, if you will, that had the strongest, highest voltage. All right, so we've kind of built on skills from lecture 1 with balancing redox equations, lecture 2 with kind of thinking about voltaic cells, and now putting a quantitative piece to it. So again, calculating E cell. So again, here's some steps to go through to calculate E cell. And again, understanding that a large positive E cell is going to be sort of the most favorable process. So, we're not going to get into delta G yet, but we sort of hinted at delta G at the beginning. Delta G being a spontaneous reaction is going to be negative. Delta E being a spontaneous reaction is going to be positive. In our next lecture, we're going to pull this all together and we're going to learn an equation that allows us to relate delta G and E cell.